So in the last couple of videos, I talked about how, doing work integrals and calculating work as a physics application is one of the most challenging parts of a Calculus 2 course, both conceptually, both in setting up the problems and things like that. Well, trig substitution is probably the most challenging integration technique that there is, based on my previous experience. It's a technique that students seem to have some trouble with, mostly because it involves trigonometric functions. But I'm here to hopefully dispel that, that belief and make it so that it's not too bad to handle these sorts of problems. Now, we've learned about U substitution so far, which has its place in identifying the chain rule. We've worked with integration by parts, which has its place in identifying the product rule, things of that nature. And this one doesn't, there's not a special there's not a special calculus rule that we're going to be dealing with. This is just going to be a very particular type of integral. And I think the best way to talk about it is to just show some examples. So before we get started, one of the most important things about this section is that we need to be comfortable with two of the most basic fundamental trig identities there are. Okay, and so you're going to want to have these ready to go in your back pocket, things that you don't even have to think about to look up in your notes or anything like that when you're working with trig substitution integrals. And the first one is just a very classic Pythagorean identity that sine squared of theta plus cosine squared of theta is equal to 1. This is one of our very first equations that we're going to want. And from this, we're going to want to remember things, for instance, like how I could rewrite this as cosine squared of theta is equal to 1 minus sine squared theta. Okay. The next one that you're going to want to know is the cousin of this particular formula, which is if I were to say divide everything through by cosine squared, right? If I were to divide this by cosine squared and that by cosine squared and this by cosine squared theta, what would I get? We're going to get our second equation, so maybe I'll label this one as the first one. We're going to get the second one that we're going to want to have in our back pocket, which is tangent squared theta plus 1 is equal to 1 over cosine squared, which is more famously known as secant squared of theta. All right, so let's get rid of this extra stuff, and I'll move this one a little closer, and I'm going to put a box around these just to kind of indicate that we're going to be working with these quite a lot in this section. So put that over here so we don't forget it. Now, the reason why we need to know these is because some of our integrals are going to look like the following. So just via example, okay, the integral that we're going to start off with, the most basic one that I can think of, is the following: 1 over the square root of 1 minus x squared, followed by a dx. Okay, now what's so special and what's so tricky about this integral? Well, we have a couple of things, right? Anytime you approach solving an integral, you should always start from the easiest method to the most difficult. So step one would be, does this have a very simple antiderivative? And hopefully just by looking at it, even if you rewrote this integral as the integral of, 1 minus x squared raised to the negative 1/2 power dx, there's not, you can't just do the power rule on this. You can't just add 1, divide by the exponents, because there's too much going on inside. There's not a U substitution I can do. I can't let U equal 1 minus x squared, because then I'd have a negative 2x that we'd have to deal with. And there's no real second function to do integration by parts with, even though we saw in the last video you don't necessarily need a quote-unquote second function. We can't let this be U. It will just take the derivative forever and ever and ever. So none of our previous techniques work with this particular sort of problem. And so the question is, what do we do now? And so here is the trickiest part of this whole thing. I'm going to start doing some wizardry and some stuff that doesn't make sense. And you're going to have to try and follow along. And after you see 1 or 2 or 3 examples, maybe it'll start making a little bit more sense. So let's just kind of dive in. The first thing that I would like to bring up is the following. Remember how I wrote this over here? Okay, I'd like you to keep this in the forefront of your mind as we work through this problem. The second thing that I'd like to remind you is back when we did U substitution, I remember that I introduced the idea that we have done substitutions before. And when I introduced U substitution, I had introduced it using the following example where I had like x to the fourth plus 2x squared plus 1 is equal to 0. And we had done things before, like saying, let's just randomly let x squared be equal to u, right? I can make this decision because then it means that x to the fourth power would be equal to u squared, and that allows me to rewrite this problem as u squared plus 2u plus 1 is equal to 0. And I could, try and make some progress in solving this side because now I have access to the quadratic formula and things of that nature. The whole point of this is I can make substitutions and do math with it as long as I eventually go back. And maybe just to kind of drive in my point, let me show you something else, right? If I were to give you x minus 1 is equal to 0 as a problem, and obviously, right, the solution to this is just x is equal to 1 as our solution. Great, okay, fine. But if I wanted to, for some sadistic reason, I could have said, let's let x be equal to anything random that I want. I could have said, let's let x be equal to Bob. And I could have rewritten this problem as Bob minus 1 is equal to 0. I could have then gotten that Bob is equal to 1. And then I could have just gone back and remembered that since x is equal to Bob, this is going to mean that x is equal to 1. And cool, I've solved the problem. I've arrived at the same conclusion as before. And using Bob is just kind of a silly thing to do. But I could have done anything. I could have said, why don't we let x, instead of x equaling Bob, what if we do something super outrageous? Let's let x be equal to sine of theta. Let's do that. And so our problem now is sine of theta minus 1 is equal to 0. And so if we try to solve this, again, why would I do this? Yeah, no one in their right mind would, but I just want to drive home the point that at any time I can make this substitution because I'm going to get sine of theta is equal to 1. And I could say, okay, when is sine of theta equal to 1? And you could say, oh, that happens when theta is equal to pi over 2, right? Sine is the y value on the unit circle. So you said, okay, well, when theta is equal to pi over 2, great. And now we use our mini transformation here, the fact that we had let x equal sine of theta, to say, oh, so that means that x is equal to sine of pi over 2 would be our solution. And that's going to give us that x is equal to 1. And again, we arrive at the solution that we thought that we would arrive at. So this is all a little bit extra, right? No one in their right mind would do this, but I'm just saying that in theory, I could redesign this problem in any way, shape, or form that I so chose, right? Like I could say let x equal whatever I want, and as long as I'm not breaking any math rules or things like that, it doesn't matter if I dress up the letter x as sine theta, as Bob, as whatever it is that you want to make it. As long as, when we're done, we go back to where we started with, we're going to get the same answer. So with that in mind, we're going to go back to the problem at hand. And so I want those ideas to kind of be stewing in your head. And the idea here is that we're going to take a very close look at what's going on inside of this square root. And what we're going to notice, or what I'm going to notice, and you may not have ever thought about this in your life, but we're going to notice that 1 minus x squared kind of looks like, what does it look like? Well, there's a reason I had you circle this earlier. It kind of looks like let's not use a highlighter. It kind of looks like 1 minus sine squared of theta, okay? Now, you're going to have to put on your funny glasses to kind of make this happen, but if you just kind of, buckle in for the ride really quick, hopefully it's not too big of a leap to say, okay, 1 minus x squared kind of looks like 1 minus sine squared of theta. And I just want to roll with this for a moment, which is that, so what you're telling me, right, we're gonna notice that, you know, this part matches and that part already matches and the minus sign matches and the minus sign here matches. So, you know, this would happen and this would actually happen. It wouldn't just kind of look like this, but this would actually happen if we had x squared was equal to sine squared of theta, right? If we made this particular choice. And how could we get that to happen? We could take this problem, right? How do we get this part to happen? We could take this problem and, kind of similar to a U substitution, but a very different process, we could say, you know, let's let x be equal to sine of theta. Okay, let's make this substitution just like we did over here on the far right side, where I could randomly choose to let x equal sine theta. It changes what the problem looks like, right? It changes what our preliminary answer looks like, but we're able to go back at the end and then get our answer in terms of x. Right, so no problem. So instead of starting in an x land and going to u land, now we're choosing to go to theta land, right? So we're choosing to say our ship to get over there is x is equal to sine theta, and that's going to take the integral that we currently have and it's going to turn it into a brand new integral over in theta land. And so we're going to kind of use a similar technique to use substitution, except the intuition for how we're choosing our x is equal to stuff is different. It's based on trigonometry now. Okay, so if you're still holding on at this part of the video, we're gonna say let's let x be equal to sine of theta, right? And if that's the case, then this means we already know this, but this means that x squared is equal to sine squared of theta. And so now we are firmly rooted in theta land. And so this integral is going to change, right? This integral is now going to be the integral of 1 over, we're going to have the square root of 1 minus, well, we don't have 1 minus x squared anymore. We have 1 minus sine squared of theta, right? That's what we have. And then dx. Now, hopefully we've done enough. Actually, here, before I say that, the whole point of this is that 1 minus sine squared of theta, we know, is going to equal cosine squared of theta. That this isn't going to be so bad because this integral is just going to become the integral of 1 over the square root of cosine squared theta dx. And the square root of cosine squared, well, that's just cosine. So we get the integral of 1 over cosine theta dx. And this, it looks something that's very almost completely doable for us, right? This would be the integral of secant. If I could do this integral, then we'd be good to go. But you may notice I said if we could do this integral. And if you've been paying attention since we worked with U substitutions, you may notice that the one thing that we haven't brought over to theta land is our dx. And so the question is, well, how do I get a relationship that turns my dx into d theta? We're going to use the substitution that we made earlier, and we're going to say, well, if x is equal to sine theta, not only does x squared equal sine squared, but this is going to make dx, right? If we take the derivative of both sides, maybe I'll do it the proper way. So if I do this the right way, right? So I need a d theta to show up. So I'm going to take the derivative with respect to theta of both sides. So I get d dx, d theta, or excuse me, I get d theta of x on the left side. I'm going to get the derivative with respect to theta of sine theta on the right side. And this is going to give us that dx d theta is equal to cosine of theta, which immediately gives us, this is the same thing as saying dx is equal to cosine theta d theta, and that is going to give us our relationship between dx and d theta. And so at this point, I'm just going to substitute out this dx that we forgot about momentarily, and I'm just going to plop in that it would be multiplied by cosine of theta d theta, right? That's what we get. And then this integral all of a sudden isn't so bad to solve. Now we have just the integral of, well, those cosines are going to cancel out, so I have the integral of 1 d theta. And last time I checked, the answer to this integral is equal to just theta plus some constant c. And so the whole point is, right, remember that we started off in x land, now we're in theta land. We've solved the integral, so this is great. But the problem now is that we need to go back to x land, right? And so at this point, to go back, we have to use, right, we have to use the shift very much like u substitution. We have to use the fact that since x is equal to sine of theta, how can I create a relationship between theta and x, right? How do I turn this theta back into something that has to do with x's? And this is going to mean that if I were to, well, how do I get theta by itself? I would take the inverse sine of both sides. And so you could write that arc sine of x is going to equal, and if you take the inverse sine of sine, we're just going to be left with theta. And therefore, this immediately gives us that our final answer is going to be the inverse sine function of x plus c. Or if you prefer, you could write it as arc sine of x plus c. And so that is our answer. That's our answer to this particular integral. And, you know, maybe you recognize this before. There have been some problems or some review problems where, you know, we've had to take the derivative of these inverse trig functions, and it turns out that, sure enough, the derivative of the inverse trig function, the derivative of inverse sine of arc sine, is in fact 1 over the square root of 1 minus x squared. Okay, so that was a lot, right? There's a lot of stuff going on. We're just going to dive right into a second example because I think, you know, just seeing a bunch of examples is going to help make things start to click a little bit sooner. Okay, so let's do another example. So for example, let's do the integral of the square root of 9 minus x squared over x squared dx. Now again, you should always run through your checks to make sure that this doesn't have just an easier way to do it. And our order of operations is 1. Can we just do the power rule, right? Is that something I could do? This clearly, obviously, is not just doing the power rule. So 2, can we do a u sub, right? That's the next easiest rule. I can't because, unfortunately, if I let u equal anything that has to do with this x squared, a 2x is going to pop out. We don't have any 2x's sitting around or even any multiples of just x. So that one's out. Could we do integration by parts, right? Could we do this? Maybe. I don't think we can, not very easily. We could try and separate this into this multiplied by 1 over x squared and try and do some wizardry there. Maybe it would work, maybe it wouldn't. I don't think that it's going to work, right? This is not as in one of those forms that we saw in the integration by parts video where we just have function multiplied by something else. We didn't really deal with rational functions too much in integration by parts. And so all of these methods kind of go out the window. But we're going to need, so to remember our trig identities from before. So I'm going to write them down. We had sine squared theta plus cosine squared of theta is equal to 1. And we got tangent squared theta plus 1 is equal to secant squared theta. Okay, and so now building off of the intuition from the last video, what we're going to try and do is we're going to hone in on the part that looks like 9 minus x squared, right? And now I'm going to change the way that we think about this just slightly, where instead of viewing this as 9 minus x squared, I'm going to say this kind of looks like, right? This kind of looks like, right, number minus, you know, something squared, okay? And the reason why I'm doing that is, again, because, you know, all of these trig identities, and maybe if I look at this first one, right, I could rewrite this as 1 minus sine squared theta is equal to cosine squared theta, right? This this identity is in fact number minus something squared, right? Now, again, the reason why I'm bringing this up is because we have to build an intuition for when to recognize that using trig substitution is probably going to be a good tool for us to try. And the idea is if you see something that looks like a number minus some variable squared, some x squared or something squared, it's a good hint that maybe we can get this thing to look like 1 minus, or excuse me, not 1 minus x squared, that we can get this thing to look like 1 minus sine squared of theta. Because if we do that, we can do some trickery, we can make some clever substitutions and turn this problem into something that involves trigonometry, which we saw in the last one actually, believe it or not, makes our lives a lot easier. So now the question is, how do we do that? Okay, well, let's see. It's not quite at that stage yet, so we're not quite there yet. But what I could do is let's work with the 9 minus x squared. And the first thing that I notice that doesn't really match is going to be this number 9, right? In order to get this to look like this identity, I need that to not be the number 9, right? We can't work with this. I don't have an identity for 9 minus sine squared. I have an identity for 1 minus sine squared. And so the first thing that I'm going to do to try and get this to look like, 1 minus something squared is I'm going to factor out a 9 from that thing. And if I factor out a 9 from both of those terms, the first one becomes a 1, right? That's what happens if you divide out a 9. But what happens if I divide a 9 out from the second term? We're just left with x squared over 9, okay? So this integral at this given moment in time is the integral of the square roots of 9 times 1 minus x squared over 9 over x squared dx, okay? You're like, Dylan, this doesn't look any better. Well, yeah, okay, sure. But at least I have the square root of 9, and the square root of 9 is just 3, so I can, at the very least, turn this integral into 3 times the integral square root of 1 minus x squared over 9 divided by x squared dx. And again, rightfully so, you might say this looks absolutely terrible, but I'm going to say let's focus back in on this bit that's inside the square root. And remember, I suggested that we start to shift our way of viewing this, as instead of it being 9 minus x squared, let's think about this as number minus something squared, because number minus something squared is really darn close to 1 minus sine squared, and that's kind of where we're headed. So if we take this bit on the inside, we have 1 minus, and remember, I want to view this instead of as x squared over 9. If I can write this, right, as 1 minus something squared, right, if I can do this, then I can kind of say, well, that kind of looks like 1 minus sine squared, and that would happen, right, that would actually happen if the thing that's being squared was equal to sine of theta, right? Because, and you're like, what are you talking about? Because if I square both sides, then I'd have the thing squared would equal sine squared. That would make this thing on the left actually equal to 1 minus sine squared, and I could start making the substitution to make my integral easier to solve. So we say, okay, well, we don't have that yet. Well, we kind of do, because if I take this, I could rewrite this as what thing squared. How could I write this as something squared? And, if you have been practicing your algebra, we could write this in the following way. I could write it as 1 minus the quantity of x over 3 squared. And now I can say, hey, look, I have 1 minus something squared. And we put on our little special glasses that says this kind of looks like 1 minus sine squared theta. And in fact, it actually would look like 1 minus sine squared theta if, right, if x over 3, right, was equal to sine of theta. Or in other words, if x is equal to 3 sine theta. Okay, so now we've kind of we've arrived at where we want to do. The whole point of this, it was to come up with the proper substitution that is hopefully going to make our lives a lot easier. So let's zoom out a little bit and make some more room. So what we have accomplished now, what we've accomplished is amazing. We now have the integral. We've taken the square roots of 9 minus x squared over x squared dx. We said, first and foremost, this thing is now equal to 3 times the integral of the square root of 1 minus x squared over 9 over x squared dx. And now we've said, look, let's let x be equal to 3 sine theta. Remember, I could let x be equal to anything, but I'm making the educated substitution to let x be equal to 3 sine theta. Now, why am I doing that? I'm doing this because if x is equal to 3 sine theta, that means that x over 3 is equal to sine theta, which means that x over 3 quantity squared would be equal to sine squared theta, and that would mean that 1 minus x over 3 squared is equal to 1 minus sine squared theta. And last time I checked, 1 minus sine squared theta is equal to cosine squared theta. So once we have that x is equal to 3 sine theta, we've already done the work that says, what does 1 minus x squared over 9 become? We've already done that. This is going to become, this is going to become 3 times the integral of the square root of 1 minus sine squared theta. Right? We already know in that square root, we're going to get 1 minus sine squared theta, again, from the work that we did over here. Right? The whole point of choosing x equals 3 sine theta was because it achieves our goal that 1 minus x over 3 squared looks a lot like 1 minus sine squared. Right? That's what's going to happen. Now, let's address the rest of the items in the room. So first and foremost, we would need to replace this x squared with something in terms of theta, and that's not too bad because this is going to mean that x squared is equal to 9 sine squared theta. So that's what I'm going to put in the denominator here, 9 sine squared theta. And now how about the dx, right? Dx is next to bat. What do we do with this? Well, if x is equal to 3 sine theta, then dx is going to equal to 3 cosine theta d theta. Okay, and so that's going to give us a 3 cosine theta d theta over here. All right, so our integral now becomes, well, let's see, 1 minus sine squared of theta. 1 minus sine squared theta is cosine squared. We take a square root. That becomes just cosine theta, but then it's going to multiply with this cosine theta here, and then the 3's on the outside are all going to multiply together. So we're going to very carefully get 9 times the integral, but wait, that 9 is going to cancel out actually with this 9 in the denominator, so wow, we actually don't even have any numbers to worry about anymore. We just are going to be left with cosine squared theta over sine squared theta d theta. Okay, now there's a couple ways to go about doing this integral, but this has shown up before in our U substitution videos. Yeah, there's a few ways of trying to go about doing this. Let's see. This is also equal to, so one of my first thoughts is that this is equal to cotangent squared theta d theta. Let's see, are there any functions that have a derivative that's equal to tangent squared or cotangent squared? I don't think so. Right, so I'm running through the steps in my head, like, is there something that has this easy antiderivative? I don't think so. And so my next step here would be, okay, well, cosine squared, that's famous for being 1 minus sine squared theta. And then in the denominator, we still have a sine squared theta, d theta. And so this sucker, let's see, what's going to happen here? I could split this up into two integrals. I have 1 over sine squared theta minus 1 d theta. Well, let's see here. 1 over sine squared theta, that's going to be, let's see, the opposite, or not opposite, the reciprocal of 1 over sine squared theta is going to be cosecant squared theta, then minus 1 d theta. And this actually isn't going to be so bad because I know that the derivative of tangent is secant squared. The derivative of cotangent would be negative cosecant squared. So this is going to make this equal to negative cotangent theta minus theta plus c. Okay, and we could double check that again, but the derivative of cotangent is going to be negative cosecant squared, so the negatives will cancel, so that gets us back to where we need to be. Fantastic. So this starting to look fairly promising, right? So just as a recap of where we started and where we came from, we started off with this crazy looking integral. We said, okay, look, none of our techniques work, but I notice I have number minus something squared, so let's fudge around with it a little bit. We fudged around with it, and we got to the point where we decided to make the educated substitution x is equal to 3 sine theta. And in doing that, it is slowly, if I haven't made any particular mistakes here, we've slowly gotten to the point where we said, okay, so this part on the inside, that's 1 minus sine squared theta. And we've been able to do a little bit of finessing. We turned our dx into stuff with d theta. We turned our x squared into something with thetas. And we've gone all the way to the point where we've actually been able to solve this integral in theta land. And just like with everything else, we need to recall that we chose x was equal to 3 sine theta. And we're going to need to try and use this to get back to theta land. Now, let's see. On the one hand, this immediately is going to give us that x over 3 is equal to sine theta, which is immediately then going to give us that the inverse sine function of x over 3 is equal to theta. So that could replace that particular value for theta right there. But the trickier part is, what do I do with this cotangent theta, right? How do I get that in terms of theta? Now, you could try to say, okay, well, if theta is equal to this, I'll just slam that in there and say that my final answer is going to be negative cotangent of the inverse sine of x over 3 minus, right, the inverse sine of x over 3, since that equals to theta, plus c. Right, you could try and say this. But this not only looks absolutely disgusting, I don't like things with cotangent and inverse sine nestled inside of each other. And not only that, we have enough experience from pre-calculus that maybe there's going to be some issues, some domain issues, maybe some range issues when dealing with the inverse sine function and popping it inside of another trig function like this. And so I'm going to suggest that we simplify this just a little bit in the following way. So the current question that we're trying to answer is, how do we get cotangent of theta to become something with x's? Right, something with x's. Right? And the key thing here is that we already have a relationship between theta and x. In fact, we know that sine of theta is equal to x over 3. And if I were to say, do this really cool thing, if I were to draw a triangle, then it would be totally appropriate to say, well, if this triangle had angle theta, then sine of theta would be equal to x over 3, right? Opposite over hypotenuse. And that would make this missing side the square root of 9 minus x squared. Now, I'm not going to do that algebra for you, but it's the Pythagorean theorem, right, that a squared plus b squared equals c squared. And so you can solve for this missing side, no problem. Now, why is this useful? Because our goal is to get cotangent for the same exact angle, for this exact angle right here. And cotangent, well, if tangent would be opposite over adjacent, then cotangent is going to be adjacent over the opposite side. And so what this is going to do is this is going to allow us to write that cotangent of theta is equal to the square root of 9 minus x squared divided by x. And this is how we finish kind of getting back to x-land. And so that makes our final answer for this integral. It's going to be negative the square root 9 minus x squared divided by x, right? Negative because there's a negative sign already, minus theta, but theta is going to be arc sine, or the inverse sine, of x over 3, and then plus c. And this is our final answer, as disgusting as this looks, right? And again, if you're doubtful, if you're not sure like how on earth that we know this, you could always do what to check your answer. You could take the derivative, and when we take the derivative of this, hopefully we would get that the derivative should equal the square root of 9 minus x squared divided by, what do we start with? X squared on the bottom? Yeah, x squared. We should get back to this. This is where we should get back. When all of the dust settles and we take this derivative, that's where we should get back, because that is the integral problem that we started with in the very first place. All right, so that's 2 examples done, the second one of which is way more involved than the first example. So let's do, let's do another one to just kind of help. Hopefully it helps and it's not driving you all absolutely insane. Let's see here. Let's do one maybe that uses the other identity we haven't used yet. So let's do the integral of 1 over x squared times the square root of x squared plus 4 dx. And again, I'm going to write down my identities, right? I'm going to write down that sine squared theta plus cosine squared theta is equal to 1. And I'm going to write down that tangent squared theta plus 1 is equal to secant squared theta. And now I'm going to take a brief moment to point something out now that we've had a little bit of exposure to working with these identities. And the one thing that I want to point out is that this top identity becomes number minus something squared is equal to a useful trig function, right? And this one is already in the form, except we have, like 1 plus something squared is equal to a useful trig function. I could have written the second one just as I had it before. I could have things squared, right, plus 1 is equal to useful trig function. I could have also written this second one as, I could have written this as something squared minus 1 is equal to a useful trig function, right? This one's a little bit different than saying 1 minus something squared, right? So now I have something squared minus 1. And the reason why I'm writing these down is, well, let me highlight them. So I have number minus something squared. I have number plus something squared. I have something squared plus 1. And I have something squared minus 1. I have 4 different variations that we could have here that all lead us to useful trig substitutions. And the reason why I have that is if I zoom out a little bit, those are going to help me identify what to do when I see x squared plus 4. Okay, I'm looking at this trig problem, or excuse me, I'm looking at this integral, and I'm saying, okay, none of my techniques work, U substitution fails us, integration by parts sucks, can't just do the regular antiderivative, we're out of options. But you notice, right now that this is our third example, we notice that I have something squared plus a number. Right, that's going to be the important thing. So we notice that I have something squared plus a number. And then now what we're going to do is we're going to go over here to our identities and say, which one of these do we think we're going to use? Which one of these looks like something squared plus a number? And the answer is, oh, well, that third one there works really well, right? Tangent squared plus 1 is equal to secant squared. And so we're going to use tangent squared theta plus 1 as our guide. Okay, so this is the general approach to how to do these sorts of problems, right? This third one. So if you're just tuning in now, then pay very close attention. So what I'm going to do is I'm going to follow the same exact process as before. I'm going to say, okay, x squared plus 4. In order to even get this to look like tangent squared plus 1, the very first thing that I would need to modify would be this number 4. I cannot have a plus 4 here. I can only have a plus 1. And so what I'm going to do is I'm just going to say that, well, if I were to factor a 4 out of this thing, I would have x squared over 4 plus 1 like so. So I said, okay, well, that's not too bad because now my integral is going to be integral 1 over, we're going to have an x squared. Then I have the square root of 4 times my x squared over 4 plus 1 dx. And last time I checked, the square root of 4, that's just 2. I can pull that out of this integral, and so we're going to have a 1/2 times the integral 1 over x squared times the square root of that x squared over 4 plus 1 dx. Now, things tend to look worse before they get better in this class, and this problem is no different. But now I have x squared over 4 plus 1. And so we said, okay, well now, since I have this, we say, okay, so, this would work. I would have a relationship between this and this if x squared over 4 was equal to what? Well, if x squared over 4 was equal to tangent squared theta, then I would have equality between these two, right? And I would therefore, have what I'm looking for. I would therefore be able to create this bridge from x-land to theta-land. So I have x squared over 4 equals tangent squared. And so then, we're just going to kind of do some backwards shenanigans. We're going to say, well, this is going to make x squared equal to 4 tangent squared theta. And this is going to make x equal to 2 tangent theta. And there it is. That's the substitution that we want to make. Now, one thing I'd like to point out here is that at this point, sometimes people ask, well, if you take the square root of both sides, Dylan, don't you get a plus or minus that shows up? And I totally agree. You do get a plus or minus that shows up. If I was just doing an algebra problem, I would say, hey, this needs to be x is equal to plus or minus 2 times tangent theta. But we're not looking to make every single substitution possible. I don't need to make both of those substitutions at once. All I need is one substitution for x that makes this statement true, right? Just like, in solving the problem x minus 1 is equal to 0, I could have done sine theta minus 1 equals 0 and solved the problem. I could have also done negative sine of theta minus 1 equals 0 and solved the problem, and I would still get the same exact thing. And so we just need one substitution that works, so I'm not interested in putting the plus or minus for these particular problems. I'm just going to pick one of them, and it turns out that x equals 2 tangent theta does the trick. So if x is equal to 2 tangent theta, now people always ask, how can I shortcut this work? There's a lot of steps. The way that you start to shortcut this work is we start to make some jumps in our head. We say we have 1/2 the integral. Now, if I'm writing out this fraction, some things that I know, the top is just going to stay as 1. If I say that we're going to make this substitution, so we say let x be equal to 2 tangent theta for our stuff, this is going to make, right, then x squared is equal to 4 tangent squared theta. And so that means I'm going to have, 4 tangent squared theta. Okay, now, what do we do with the stuff inside of this square root, right? How do we, what am I, wrong color, or wrong thing. What do I do with this x squared over 4 plus 1? Well, the whole point of making this substitution x is equal to 2 tangent theta was that we know that x squared over 4 was equal to tangent squared. And that would make x squared over 4 plus 1 equal to tangent squared plus 1. So I already know from all the work I've done before, I don't have to go through and do it all again. I know that x squared over 4 plus 1 is going to become tangent squared plus 1. It's going to become tangent squared plus 1. And I know tangent squared plus 1 is secant squared. But I'm taking the square root of secant squared, so I'm just going to have, when all the dust settles, I'm just going to have secant of theta there in the denominator. And the last bit that I have to do is I need to cover this dx. And so we're just going to use this to say, well, this is going to give us that dx is equal to 2 times the derivative of tangent, which is secant squared theta. And we'll have this d theta, which, again, I'm shortcutting 1 or 2 of the steps here. We are supposed to just take the derivative with respect to theta of both sides and then separate things. But with enough practice, we can just start to make this jump. So then I'm going to have multiplied by 2 secant squared theta d theta. Okay, and now this integral is something that looks a little bit better. Let's try and see how far we get. So I have, let's see, I've got some numbers. Let's see, so I have a 1/2. That's going to cancel out with this 2, and then I should be left over with a 4. So I think I'm going to have a 1/4 in the front. One of these secants is going to cancel out, so I'll have an integral of secant theta over tangent squared theta d theta. And at this point, I don't really care to work with, secants and tangents and stuff like that. I much prefer working with sines and cosines. So that's what I'm going to do. I'm going to write this as 1 over cosine theta divided by, and then the bottom we're going to have sine squared theta over cosine squared theta d theta. And hopefully we remember that to divide by a fraction is the same thing as multiplying by its reciprocal. So this is 1/4 times the integral of 1 over cosine theta multiplied by the reciprocal of the denominator. So cosine squared theta over sine squared theta d theta. And this integral is 1/4 times the integral of cosine theta over sine squared theta. And thankfully, this integral is actually fairly straightforward and fairly easy to solve. This one just requires a u substitution where we do u is equal to sine theta, du is equal to cosine theta d theta. This turns our integral into 1/4 the integral of 1 over u squared d theta. That becomes 1/4 the integral of u to the negative 2 d theta. And going all the way up here, we're going to get, let's see, so add 1 to the exponent, divide by the new exponent. So we're going to get a negative 1/4. And then, so add 1 to the exponent, divide by the new exponent is just going to be a u to the negative first plus c. And so now we're done. We've solved the integral. So we have negative 1 over 4u, right? That should be that. But what did u equal? U was equal to sine theta. And that was a substitution we made, so plus c. And now we just need to go back to x-land. And now we're stuck in kind of like the same thing that we were in before, which is, here's my answer that I've solved for in terms of theta. How do I get back to x-land completely? And we can use the fact that we chose this substitution that x is equal to 2 tangent theta. And we say, well, using x is equal to 2 tangent theta, that implies that x over 2 is equal to tangent theta. And so again, I could just build myself this cool little triangle that has an angle of theta in it, right? There's my angle theta. I happen to know that tangent, which is opposite over adjacent, is equal to x over 2. That would make my, my hypotenuse the square root of 4 plus x squared. Why do I care about that? Because my goal is to get sine theta in terms of x. And so from here, we get that sine, which is opposite over hypotenuse, is going to be -1 over, and then we're going to have a 4 multiplied by our opposite over hypotenuse, square root of 4 plus x squared, and then our plus c at the end. And we can tidy this up a bit in the same way that we just did, which is dividing by a fraction is the same thing as multiplying by its reciprocal. So what do we have? We have negative square root 4 plus x squared over 4x, and then plus c as the dust settles for our absolute final answer, like so. Okay. So that's gonna be 3 worked out problems for trig substitution, and I think this is a good place to stop. We've kind of gone from easy to I wouldn't even say medium. I'd say upper medium, and then maybe hard if you consider using a different trig identity hard. But I think at this point we've covered the main meat of it, which is that we're going to be looking out whenever we are working with these sorts of problems. We're looking to identify any point where we get, something squared plus a number. The only other thing I could think of that would be slightly more complicated than this, which I'll leave to do for, let's say, the homework, would be what if I had 1 over, like, the square root, and I had 9 minus 4x squared or something like this. Right? And we say, okay, well, this kind of, it kind of looks like, and by it, I mean this chunk here, kind of reminds me of the 1 minus sine squared identity. That's going to be equal to cosine squared theta. So I'm going to use that as my guideline, and I'm going to do the same process. I'm going to say, well, I can't do anything if the number here doesn't even match. So I'd say, let's factor out that 9. And the only thing that's different here is, well, if I factor a 9 out of the first term, I'm just left with 1. What would I be left with in the second term if I divide out a 9? I'm just left with 4/9 x squared, like so. And now that we've handled that part, where now the ones match, we have a green light there. We're trying to now identify, okay, what do I do with this chunk? How do I get it to look like sine squared? And you say, well, they'll look the same if 4/9 x squared is equal to sine squared theta. We do a little bit of mathematical finessing. We'd get something like x squared is equal to 9 over 4 sine squared theta. And that immediately lends us saying, oh, so if we were to let x be equal to 3/2 sine theta, then this would happen, then this would happen, and then this whole thing would be equal to the 1 minus sine squared theta that we came up with. And then we keep going. The problem keeps going. So this would be like the maximum, most challenging sort of problem that you could possibly ever get for this particular material. So what I would suggest doing is to pull up any homework that you have alongside this video, and to try out 1 or 2 of the problems while also having this video kind of close by to help you, as you kind of journey your way through this particular topic. If you get stuck, post questions in the discussion. If you feel like you need more worked examples, check out the textbook for more examples. But I think that these 3 examples plus the last one I just showed you do a really good job of really illustrating this really cool, this really clever this process for solving these integrals that involve like number minus something squared. I think it's pretty slick. So if you run into any trouble, post questions in the discussion, shoot me an email. But other than that, hopefully you thought this was pretty interesting. And once your brain is back down on Earth, feel free to hop into the next video.